Hello everyone, I hope all of you are doing good. In this video, we'll talk about very interesting topic in general organic chemistry. Today we'll talk about the arrows and their importance in representing the organic reactions. As we know, we are writing chemical reactions. We are representing the reaction mechanism. And if we are writing and representing these reactions without the help of text, then we are taking the help of arrows and chemical structures only. But while representing these reactions, if we are not able to represent the proper arrows or the structures, then we may not get the exact idea about what we are trying to explain or we are trying to represent. As the chemistry is all about the formation and the cleavages of bonds, and also it involves the movement of electrons from one center to another center. All these things we need to represent with the appropriate notations. And these notations in chemical reactions, they are represented with the arrows. As we know, the chemical reactions, they are nothing but a transformation of reactants into the product with the help of different chemical environment that we are using related with the reagent, solvent, catalyst, and other reaction conditions. So that helps to transfer the reactants into the product. And that change or the chemical environment we are providing, and that is responsible for the overall transformation with stepwise understanding to get the involvement or movement of electrons from one center to another. All these things that we are representing in a chemical reaction, we are using with the help of arrows. The arrows that you are seeing on the screen, they are used for the specific purpose, and this representation is really helpful to understand and write the things in a very specific manner. So the objective of this video to understand all the things about these arrows and the chemical reactions in detail. And definitely this video will guide all those students who are facing the problem with representing the reactions, specifically the reaction mechanism as such, and they will be definitely benefited by the understanding about all these arrows in detail. So let us start with the first arrow. The first arrow is it is called as a forward arrow, or it is also called to be a chemical reaction arrow. It is represented with the straight double bar arrow. It means it is having this two bar. The meaning of this two bar is associated with the involvement of direction of reaction. That means if you are starting with this state, more specifically, this is nothing but a reactant, and it is ending with the head, that is the product side. This is the reactant side, and this is the product side. And while doing so, the thing that, as we discuss, it is the involvement of all the reaction conditions such as the reagent, if we are using the catalyst, temperature, duration of chemical transformation, as solvent, and any other thing that we are using for this particular transformation that we are writing along with this. This arrow is used if we are writing the single step conversion or the multi-step conversion, and overall reaction can be represented by this transformation, that is the reactant is getting converted into the product. Let's talk about the simple example. In this case, as we are observing, this carbonyl group on the treatment with the sodium cyanide, it is getting converted into cyanohydrate. This is a single step transformation. If we are getting this presentation, we are getting all the idea about how the reactant is reacting with this, and we are getting the product. That's it. In the second example, you'll find this is a two-step conversion. In the first step, as we know, this is the carbon-carbon bond formation between a carbonyl group and the grignard, and the second step that involves the workup. So if we are writing or we are getting the representation of this particular reaction, we can indirectly getting the idea about this is the two-step reaction that involves the first step is the carbon-carbon bond formation and the second one is the workup. In third example, we are observing this is a stepwise conversion of reactant into the product through the multiple steps. And every step, we are getting the idea about the how the individual uh, intermediate is formed and all the details about the reagent. So overall, forward arrow at the chemical or the chemical reaction arrow is nothing but it is guiding us to understand the reactant side and the product side. Along with this, we are also getting the idea about the description of reaction regarding the what is the reagent catalyst and the reaction conditions that are in place for this transformation. Let's talk about the second arrow. The second arrow is nothing but it is an equilibrium. If we are thinking that chemical reactions, let's say if you're starting with A and we are getting the B, does it mean that we are always moving in the forward direction? And if this question is in someone's mind that if we are doing the reaction and reaction is only moving in the forward direction, there is no possibility that it is coming back, then I think the equilibrium arrow will guide us. This arrow is represented with the two half arrows. Half arrow is a concept that is indicating this single bar, and if it is a two as it is a two half arrows and they are in opposite direction, it is represented like this. It is represented like this. It means this particular transformation is nothing but it is involving the reversible reaction. It means this is nothing but it is a forward reaction as it is moving from this to this, and this is nothing but this is a backward reaction that this is moving from the product side to the reactant side. On the basis of the transformations, it is divided, or the equilibrium arrow is representing the three important things for us. It may be involvement of a dynamic equilibrium, or it may be showing us the involvement of product favoring equilibrium, or the third thing is it may be associated with the reactant favoring equilibrium. What is the meaning of this? Let's talk with the first example over here. In this example, we are seeing this is a simple transformation of ester. This is ester functionality, and the final product is the carboxylic acid. So in this overall reaction, we are observing the conversion of ester to carboxylic acid in presence of this acidic medium. So if we are using this equilibrium arrow over here, what is the meaning of this and what kind of information that we can describe? So overall, this transformation we are observing that this is passing through the different intermediates. All these intermediates are guiding us. Again, this is another intermediate, and this is the third intermediate. So all these intermediates that we are seeing, that for example in this case the ester is getting protonated as subsequent attack of the water molecule, and finally we are getting the carboxylic acid. What is the meaning of this equilibrium arrow? As the ester is forming the different intermediates, and this intermediate is able to get convert again to the ester, or this all intermediate. For example, this is intermediate 1, intermediate 2, and intermediate 3. Then these intermediates, that is 1, 2, 3, they are having equal probability that they can get interconvertible in this acidic medium. And so the reaction is moving from ester to intermediate 2, and then intermediate 2 and intermediate 3, and finally it is getting converted into the carboxylic acid. So the reaction is moving with the constant equilibrium between all these intermediates, and the maintaining the concentration of these intermediates. The reaction is passing through the sequential transformation. So overall, This reaction, even though looks to be simple, that the ester is getting converted into carboxylic acid, but it has to pass through all these obstacles and then we'll get the product. So that is the meaning of this. And here we are using those indications where the forward arrow and the backward arrow, they are with the equal length. It means all these possibilities of conversion of these intermediate structures is equally possible. So they are having the possibilities that the interconvergence can be easily get convert from one structure to another structure. But another two things that it is related to the either product favoring or the reactant favoring equilibrium. Here we'll find in the second example, this is nothing but example of amino acid. This is the amino acid. As we know, the amino acid is nothing but it is such a moiety that is associated with the two functional groups. First one is this is the amino group, and the second one is the acid, carboxylic acid group. So as we know, amino acid is having one of the very characteristic property that it will be in the form of a deuterion. So it is since involvement of two functionalities in the same molecular structure, and this is a basic in nature, and this is acidic since it can easily give H plus, and this will pick up the proton. So this is the intramolecular acid base reaction, and that leads to form the deuterion. So while representing this equilibrium arrow where we are finding the forward and this is a backward arrow that we are observing, the forward arrow that is with the longer length, it means the possibility of formation of deuterion over here is more compared to the backward direction. That means this is a quite stable form compared to amino acid, and therefore the forward arrow is shown with the longer length. On the contrary, in the third example, we are observing that the interconversion of tautomerism between the keto and the enol form. Here, the forward arrow, and this one is the backward arrow. Here we are observing the backward arrow that is with the longer length compared to the forward arrow. It means the keto form is more stable compared to the enol form. And therefore, we are observing there is a probability that the keto form will be in a major extent or in a major percentage compared to the enol form, and therefore this equilibrium arrow is represented like this. So overall, if we are observing or wherever we are seeing such transformations in any book or any kind of explanation or anything related to the question, that equilibrium is there, and the equilibrium may be in the form of dynamic equilibrium where the probabilities of interconversion is equally possible. So it will be represented with the equal lengths of the forward and the backward arrow. But in the case of this second and the third example we are observing, it may be either favoring the product side or it may be favoring the reactant side. In this case, only the thing or the difference is with respect to the length of either forward arrow or the backward arrow. Third arrow is, as we know, it is one of the most common representation of resonance structures, and it is called as a resonance arrow. All the resonating structures we are writing for common conjugated system that we need to represent with the resonance arrow. It is a double headed arrow and it is a straight arrow. What is the meaning of this? What is the meaning of the double headed arrow? As we are representing the arrow, simple arrow that is with this is with the double bar head, and if we are having the second side of this arrow again with the same indication of the double head, double bar, so it can be represented like this: the arrow which is having this two head, this is one head and this one is the second head, and therefore this is called to be double headed arrow. and both the heads, they are with the double bar. They are with the double bar. What is the meaning of this? This is guiding us to understand the different resonating structures. What are the resonating structures, by the way? Let's have the simple examples. If we are having the simple structure like acetone over here, as we know, this is the pi electrons and there is a delocalization is possible. So the electrons may get delocalized from this double bond to the oxygen and we are getting this structure. Similarly, in a benzene also we know this delocalization of these electrons is possible, and we are representing the structure like this. But the structure first and the structure second, this is represented in a way so that the structure first and structure second, they are identical, but only the thing is the location of electrons is changed, and these two resonating structures, they are represented with this resonance arrow. As we know, we are having the also possibilities that the involvement of electrons shift from the ring towards the electron withdrawing group or the electron donating group can be also represented with the resonating structure. Here we are observing the electrons as they are moving from this ring towards the electron withdrawing group over here, and we are seeing the formation of the carbocation, and this carbocation will be delocalized with the help of resonating structures, and all these representation of resonating structure can be shown with the help of this resonance arrow. So resonance arrow is nothing but that guide us to understand the different possibilities of structure that are formed through the resonance. Next arrow is very important as far as the reaction mechanism is concerned. As we discuss, wherever we are representing the chemical transformations, it is important to understand how the electrons they are moving from one center to another center. And for that reason, we also need to understand the concepts, that is electrophile and the nucleophile. As the electrophile is the species that is it is looking for the electrons. It is electron deficient species, while the nucleophile is the species that is electron rich. It can easily give the electrons and it will try to form the bonds, and through this either the as the electrophile is accepting electrons and the nucleophile is donating the electrons, so it is a complementary form of reaction mechanism and they are getting the stability. How we can represent the involvement of or the reaction between the electrophile and the nucleophile? This is represented with the curve or the curly arrow. In this case, they are also of two types. The first arrow here that we are discussing, it is a curly arrow or the curve arrow with the double bar. As we have already discussed, the double bar, it is nothing but it is involvement of this two barb structure, but it is a curly. It is not like the straight arrow that we have seen earlier. It is a curly or a curve and with the two bar. What is the meaning of this two bar? It is involving the movement of two electrons. As we know, the electrons are moving from one center to another, and we are leading that leads to form the different intermediates such as the cations or the anions. As we know, the overall chemical reaction can be represented with the either ionic reactions or the radical reactions. So if it is involvement of two electrons, then it will lead to form the ions. How the ions are we are getting in the chemical reaction, that can be also understood with this transformation. Let us talk about the first example. Here we are observing this is a acid, carboxylic acid, and this is a base, hydroxyl ion we are observing, and on the right hand side we are seeing the formation of anion and this neutral water molecule. What is the reaction? How we can represent this simple transformation? Since this is the basic in nature, as this is a nucleophile, so this is the electron rich species, and this is the acid which is a source of H plus. What is the simple reaction over here? So we can represent like this. This OH, it will pick up this proton as the oxygen or with the negative charge. It will give both the electrons to this H, and this OH bond will be heterolytically cleaved, so that the new bond formation between the oxygen and hydrogen that leads to form this water molecule, and the heterolytic cleavage between this OH that leads to form this anion. So the simple transformation of electrons from the oxygen to hydrogen, and the cleavage of this OH bond, and both the electrons from this OH bond will be shifted toward the oxygen, and the formation of the anion over here. So this is the simple reaction that can be represented. Let's talk about the second example over here. In this case, the carbonyl group is reacting with the sodium borohydride. This is a source of hydride, H minus. This is a source of a hydride. So what is the reaction over here? How we can represent the formation of the new CH bond formation? So the, as we know, the sodium borohydride is a source of H minus. So in this case, one of the BH bonds will attack on this carbonyl group, and the electromeric shift that will lead to form this oxygen anion. So how we are representing this? Both the electrons from this BH bond, they are getting along with this hydrogen, and we are calling it as a hydride. And this hydride is attacking on a carbonyl group to form the new CH bond. And with this new CH bond formation, electron is shifted from this carbon oxygen double bond to form this anion, and that leads to the CH, and afterwards with the workup that will get converted into the OH. So this simple representation can be useful to understand overall transformation to get this basis, and we are showing this transformation, or we need to show this the reaction mechanism with the curve arrow that is involving the involvement of two electrons. Here the BH bond is also involving the two electron shift, and the carbonyl group, both the electrons of this double bond, they are also shifted toward the oxygen, and that is also involvement of two electrons, and therefore we are using this double bar arrow. In third example, as we know in the resonating structure we have seen, if we are showing the involvement of the electrons, these two electrons they are moving, so therefore that representation is also shown with the curve arrow with the double bar. Next arrow is again it is a curve arrow, but in this case it is showing the involvement of single bar, or it is also called to be the fishhook arrow. What is the meaning of this? As we have seen earlier, that if we are showing the single bar, as earlier case we have seen the double bar, but in this case we are representing a single bar. And this single bar, that is nothing but, here we need to understand the movement of single electron. As we have just discussed, the electrons, if they are moving, either there may be involvement of single electron or the two electrons. And overall reaction mechanism, it may be of two types. It may be either ionic reaction mechanism, or it may be associated with the radical reaction mechanism. As we have seen earlier, the ionic reaction mechanism, for that reason there is involvement of two electrons as such. But the radical reactions, wherever we are getting the radical reaction, it is involvement of one electron, and this involvement of one electrons can be represented with this curve arrow with the single bar. Most of the time, the all homolytic cleavages and the radical reactions, they are represented with this. The simple reaction that we are observing over here, the homolytic cleavage. The homolytic cleavage, as this chlorine molecule is composed of these two electrons. As this is the covalent bond, it is involved. It is formed with the involvement of two electrons. If we are showing the homolytic cleavage, then we need to show this single barbed curve arrow indicating the both the electrons which are forming this bond, it is getting cleaved in a way. Both the chlorine atoms, they will get one electron each and it will form the radicals. So radical formation is shown with this arrow. How we are using this particular radical formation reaction or the single barb this curved arrow in a reaction mechanism that involve the radical reaction over here. So let's talk about this example. And this is a peroxide. As we know, the oxygen-oxygen bond is it's quite reactive with as it is involving the weak bonding. So if we are representing this reaction mechanism in a photochemical reaction condition, it will show the involvement of this homolytic cleavage, and homolytic cleavage that will lead to form this radical. That will lead to form this radical. As this peroxides generally they are used as initiators, and once these radicals are formed in this reaction, this radical will initiate the reaction. It will initiate the reaction. That means it will start the reaction. So this hydroxyl radical, it will react with this hydrogen bromide, and the hydrogen bromide is again, as it is formed with the involvement of two electrons. So this HBr molecule will again, it will get homolytically cleaved, and this hydrogen will share one electron with itself, and it will get out of the system as H dot, and the Br again it will come out of the system as Br dot. So here the formation of the water molecule, as water molecule is formed because the hydroxyl radical, it is sharing one electron from the oxygen side and one electron from the hydrogen from the HBr, and that will form the water molecule. At the same time, it is forming the Br dot or the Br radical acids. And this Br radical, it will propagate or it will continue the reaction. So here we are observing this Br dot or the Br radical, it will react with the alkene, that is our reactant. So here the Br dot, it will give one electron, and this alkene, as this is alkene, as we know, this is associated with the carbon-carbon double bond. So again, the pair of electrons which is forming the double bond, it will share one electron. The carbon will, this terminal carbon will share one electron, and this internal carbon will carry one electron. So there is a formation of new carbon Br and the bromine bond over here, and this internal carbon it will be with the radical, and again this reaction will get propagated, that this radical again it will share one electron, the new HBr molecule it will share one electron, and there is a formation of new Br radical, and this reaction will get continued unless all the molecules of alkene will get converted into a this addition product, that the HBr is getting added across this double bond. So overall such radical reactions or the homolytic cleavages are shown with the curve arrow. And as we discuss, all the representations of these reactions that we need to understand with respect to the proper use of arrows. Many of the times students, they when they are representing the involvement of single electron, they are wrongly representing the double barb arrow, but that is not the correct one. Wherever there is involvement of single electron, we need to take the help of a curved arrow with a single barb. That is the thing that we need to understand, and that is the reason why, if you recall, the title of today's representation is something related to the mind the arrows while representing the chemical reactions or reaction mechanism. Next arrow is something related to the retrosynthesis arrow or retrosynthesis as such. This arrow is guiding us to understand how we can form or synthesize some complex molecules. And for that reason, we need to get into the idea about the synthesis as such. But before to this, we'll just talk about the representation. This arrow is represented like this, as This is guiding us about how the synthesis can be taken place, or how we can design this. So before to this, just we'll have a small discussion about the synthesis as such. As we know, suppose we are having the two different substrates A and B, and we are getting the product. So simply we are describing that we are doing the synthesis of this product. Let's say product X. We are synthesizing X from A and B. So this is the simple thing that we are writing with the help of this forward arrow, as we have seen earlier. But suppose if someone will ask you how will you synthesize the product, then the simple thing can be represented like this. The product, as we know, this can be synthesized from A and B. That's it. So this is the synthesis that we are representing, that A and B, they are forming the product, and this is a retrosynthesis. So synthesis is nothing but it is a transformation of reactants into the product, while the retrosynthesis is a mechanism or understanding how the product can be synthesized, and for that reason we are using this arrow. This arrow is giving us idea about how the product can be formed, and in this case we are observing that the product can be synthesized from the two simplest possible reactors. Most of the complex or the simple molecules, they are used or they are represented with this retrosynthesis arrow. Let's talk about this simple example so that we can understand it in a simpler way. As this example we are observing, this is nothing but amide. How we can synthesize this amide? For that reason, if we are starting with this simple molecules like this is the amine and this is the acyl chloride. If you are reacting this amine with this acyl chloride, then of course, as we know the reaction mechanism, this nitrogen will attack on the carbonyl group and this Cl will get displaced, and there is a formation of the new carbon nitrogen bond. So overall, this is the target molecule or our product, and this is represented like this, that this target molecule can be synthesized from this two simplest possible substrates. So retrosynthesis arrow or retrosynthesis representation is shown with this arrow, and this is guiding us how the complex or the simpler molecules can be represented with the possible substrate. And this is the way that is giving us the idea about the synthesis. And this representation is nothing but it is related to those particular practitioners of chemistry which are dealing with more complex molecules. If it is associated with the simple transformation, we can easily identify the possible substrates. But suppose we are dealing with some complex molecules, then we need to understand what are the possible substrates. For example, in other examples, A and B may be some complex molecule. Again, we need to think about how the A can be synthesized or B can be synthesized. So we need to keep on doing these practices until we are reaching to the simplest possible reagent. So again, we need to think about how A can be synthesized. So how B can be synthesized. So this process will get continued unless we are reaching to the simplest possible substrates. So this is all about the retrosynthesis arrow. Next arrow is something related to the mentioning about the failures. It is something related to the mentioning or underlining the failure in a chemical synthesis. As we know, we are dealing with the chemical transformations. Many of the time we are writing A is getting converted into B. It's a very good to listen that every time we are getting the success. But many of the time there is a possibility that while doing a number of atoms, we are doing this reaction number of times, but the overall result is will not get the product. Whatever the reaction condition, whatever the atoms we are performing, but we are not getting the final product. So how we can describe this? So this is represented with the simple uh, uh, representation that this forward arrow, this is indicating that we are expecting the transformation in this way, that this is a reactant and this is the product. But while doing or while attempting the number of atoms, this reaction does not happen, and this will not happen because there may be reasons with respect to the basic structures, or it may be related to some inappropriate reaction condition that the one who is representing the reaction. So for example, if I'm doing the reaction, that if I'm expecting the substitution of fluorine by the Br using the KBr, so even though I will try it number of times, I may not get it. The reason may be simple, that if I'm expecting the displacement of fluoride by the Br, technically it is not possible. So even I'm attempting it number of times, the reaction will not happen. So overall, I will represent the reaction that if this is the substrate, if I am doing this reaction with the help of this reaction condition, and I'm expecting this product, this reaction is not working. So this is shown with the chemical arrow. As we know, the chemical arrow is this one, with the centered double hash, that I can represent like this. The reaction is not working, or I can show like this, that this reaction is not working even though applying the number of atoms and the reaction condition. So this is called as a broken arrow, or this is representing the, as I said, it is something related to represent the failure in a chemical reaction. Next two arrows, they are important with respect to understanding the observations. As we have seen earlier, that this chemical transformations, they are associated with converting the reactants into the product. And many of the times that while doing the reaction, there are certain observations, and these observations has to be documented so that the person who is doing the reaction next time, that person will get the idea about this. What are the observations? As in this first example, we are observing that simple carboxylic acid, when we are treating with 10% sodium bicarbonate, uh, simple observation we are getting, that we are observing the effervescence of one gas. We are observing the carboxylic acid when we are treating with the 10% sodium bicarbonate. We are observing the effervescence of gas, and this gas is nothing but it is a carbon dioxide. And while representing this, we need to take the help of upward arrow. At this, whatever the gas that is getting formed in a chemical reaction, it is notified with this the carbon dioxide, and it is with the upward arrow. It means the gas is formed in the system, and that is we need to mention with this upward arrow. What is the importance of this? If we are doing this reaction, let's say on a 10 milligram, then there may not be the too much significance about the gases getting released. But suppose we are doing this reaction on, let's say, 1000 kilograms, then we need to be more cautious, because if this reaction will be done on a commercial scale, on large scale, then whatever the amount of carbon dioxide will get released, it will be a huge one. So for that reason, if we are not mentioning the observation with the appropriate uh, notation, so that the person who is doing the reaction will not get the idea that the gas is getting involved in this reaction, and we need to be more careful about designing the reaction on a large scale. So this is, even though looks to be simple, but this is a valuable. Next arrow is it is a downward arrow, and this is exactly opposite to the first arrow, that is related to the gas. In this case, this is something related to the precipitation or the solid formation in a chemical reaction. As the this is a salt of carboxylic acid, when we are doing a protonation of this, we'll see that in a chemical reaction the solid will get formed in the reaction, and this is insoluble in a reaction condition. So we are observing the formation of solid. Again, as I mentioned, this is something related to the observations. So this information we are getting from the particular arrow, that this arrow which is shown by the downward direction, it is indicating that some solid is formed in the chemical reaction, and that we need to mention with the appropriate notation. Both the things, that is, let it be the upward arrow or the downward arrow, they are indicating the key observations in chemical reaction, and with the simple representation we are getting this information. So arrows overall, even though we are not writing in this reaction, also we are observing, we are not describing anything, we are not writing any kind of text to represent this, but by just looking toward this, in this simple representation, we are getting the idea of the, we are starting with the reactant, we are using the different reaction condition, we are showing the forward arrow, we are getting the product side, and the product side we are observing that something is getting out of the system in the form of either solid or the gas. So all these representations we are getting with the help of simple arrows and the chemical structures. So overall arrows, they are very crucial, and they are very much important as far as the chemical transformations are concerned, or with respect to the understanding about the detailed or the stepwise conversion of particular centers with the involvement of either a single or two electrons as such. So I hope that this video you may find very interesting with respect to understand the chemical reactions as such, or also with respect to understand the overall chemical reaction mechanism in organic molecules specifically. If you feel that this video is helpful to you, I request to share with your friends, and subscribe the channel if you are not subscribed earlier. And most importantly, if you find that this is very helpful material for your studies, please keep your comment and keep writing us, so that I will also come to know about what exactly the thing that you are expecting from my side. At this moment, thank you so much for watching the video. Take care.